So first of all, it's a really great pleasure to be here with you among so many old and new friends to visit. I have been here many times, and many of you in the audience I've had the pleasure and the privilege of collaborating with over the years, and it's really my pleasure to be here, and I thank you for the invitation. As you can see from this first slide, I'm going to be talking about lessons that we can and should have learned from COVID-19 and how that might help us in our pandemic preparedness and response for the inevitability of future pandemics, which without a doubt we will be challenged with. But before I get to the lessons learned, let's just spend a few minutes to give a little bit of a background, a summary of where we are now and how we got to where we are, so that we can actually pull back and talk about lessons that we can and should have learned. As many of you know, in January of 2020, a novel coronavirus was discovered in association with a cluster of pneumonias that were identified in the central Chinese city of Wuhan. Very quickly, the Chinese identified this as a coronavirus, and literally within days, the sequence of that coronavirus was made public in a public database done by an Australian scientist, Eddie Holmes, as well as a Chinese scientist, Professor Zhang. So literally within days, and this is very important when one thinks about our ability to identify and move on a particular pandemic, which I'll get into in a moment, is so important in an adequate countermeasure response. For those of you not familiar with it, this is a coronavirus phylogenetic tree. And the red font are the coronaviruses that have been known to infect humans. Those here at this part are the common cold coronaviruses that everybody in this room, for sure, has been infected with since the time you were children. However, in 2002, with SARS-CoV-1 was the first recognizable pandemic, as small as it was, associated with the coronavirus. It was 2002, 2003. There were 8,000 cases and 781 deaths. Because of the lack of efficient transmissibility from person to person, this particular coronavirus outbreak was able to be contained by classical non-pharmacologic interventions: identification, isolation, and contact tracing. In 2012, we had MERS, a much less challenging coronavirus, again, that emerged from an animal reservoir. The SARS-CoV-1 was from a bat to a civet cat to a human, the interface between animals and human. And MERS, which arose in Saudi Arabia, was from a bat to a camel to a human. So the historical precedent for an animal reservoir switching over to human in a coronavirus has been there for at least a couple of decades. And then, as I mentioned a moment ago, in the end of 2019, January of 2020, we had the SARS coronavirus. So let's look at what evolved over the next few weeks. In the United States, on January 21st, the first travel-related case of a novel coronavirus, which we're now calling SARS-CoV-2, was seen in the state of Washington in the northwest part of the United States in someone who traveled from Wuhan, hence travel-related case. A few days later, the first travel-related case was noted in Italy. and again in a person who had traveled to Wuhan. And that was the very beginning of what we've all experienced in an extraordinary manner over the last 3 years. Fast forward 3 months to March of 2020, the WHO declared that we were dealing with a pandemic. At that time, there were over 100,000 cases in over 114 countries and 4,000 deaths. So just pause for a moment. At that point, it was designated a pandemic with 4,000 deaths. And just reflect for a moment what's happened over a period of 3 years. We had no way of knowing then the enormity of this problem. I get asked that all the time. Back in March, did you ever imagine that we would be in the situation that we were in now? And the answer is obviously no, because what we've experienced has been a pandemic, the likes of which we have not seen in well over 100 years. So let's fast forward now from March 2020 to a few days ago in 2023. There are over 700 million reported cases, a dramatic underestimate, because reported cases, most of the cases don't get reported. There have been about 7 million deaths. Again, a gross underestimate. The estimate is likely closer to 20 million deaths. It is very interesting that when you ask people who have been infected and vaccinated whether or not they've actually reported their infection. So if I would ask the audience, how many of you who've been infected actually officially reported your case? Okay, how many have not reported your case? So that's the reason why it's a gross underestimate. Okay, so let's move forward. Of particular interest for today's discussion, that when you look at the confirmed deaths per million people, the United States and Italy are very strikingly similar. In the United States, the number was 3,300, and in Italy, it was 3,200. But the dynamics of the outbreak were really different from the beginning to the end. Let me show you. First of all, if you look at the deaths on a 7-day rolling average throughout the world, it is very, very clear that we have had waves of infection. The first break, and then Alpha, Beta, Gamma, Delta, and then Omicron, and now here's where we are. So I just did a press conference with a couple of Italian press, and they asked, is the outbreak over? I'm going to get to that a little bit later on in the talk. But the one thing I was able to say with confidence is that we are much, much better off now than we were in 2020 and 2021. Now, if you look at the comparison of Italy and the United States, it is no secret that Italy was the first Western country, certainly the first European country, that got hit very, very hard. And that was right here where you have Italy in red, and the United States followed, particularly in New York City, very, very soon thereafter. It seems that what happened in Italy happened in the United States 1 month later. So we would use Italy as sort of our gauge, because if you look at it here, except for Delta, the United States got hit much, much worse with Delta than did Italy. However, look how similar our responses are to the Omicron variants, that up to this day, there's a great deal of similarity between Italy and the United States. Now, again, I got asked 3 times in the last hour by the Italian press, is the outbreak over? Is the pandemic over? Well, it depends on what your definition of over is. Certainly, the WHO and the United States has declared it is no longer a public health emergency. But we still have enough cases that it isn't completely behind us. And I'm going to get to that in a few minutes when we talk a bit more about the lessons learned. So with that as a background, let's take a look at lessons learned. Now, I picked out 10 lessons. There are probably 50 lessons that we can learn, but since I want to make sure I don't bore you with too many of the granular ones, let me pick out what I think are the 10 most important lessons that we've learned. First, expect the unexpected. What do I mean by expect the unexpected? Many aspects of SARS, the virology, the transmission, the pathogenesis, all of that were not expected or initially appreciated. What do I mean? First, we are dealing with a highly mutable virus that evades immunity, therapy, and vaccines. We don't fully appreciate. We've been through pandemics of influenza, outbreaks of other diseases, but never in the history of virology, in the same outbreak, have we had multiple variants of a virus that have evaded immunity. And that is very, well, for those of you who don't like family trees, bear with me, this is really simple. And that is, this was the original Wuhan strain here. And for a period of a few years, we had different variants, alpha, beta, gamma, delta. Then what happened in the winter of 2021 is we had one variant that was dramatically different than the others, and that's Omicron. And that's the reason why when we thought we were over with it, we got surprised. And that's why I say expect the unexpected. Because when Omicron came, that was, I remember, it was Thanksgiving Day of 2021. It interrupted my Thanksgiving Day meal when the South Africans called me up and said, we're dealing with a brand new virus that's very, very different. And the reason is that ever since then, everything we've had have been sublineages of Omicron. Right now, the dominant one in the United States is XBB.1.16, and it will keep going on. But the good news is it's similar enough that the protection that you get from vaccines and from prior infection may not protect you against infection, but it does a very good job in protecting you against severe disease. And that's been the story of vaccines. I'm sorry. So one of the characteristics of the virus is that every time you have a new variant, in a stepwise fashion, it has a greater growth capacity and a greater transmissibility to evade prior protection. And that's the thing that confuses people when they say, does the vaccine really work? It works extremely well in protecting you against severe disease, but as you get more variants, it is less protective against initial infection because you need a high level of antibody in the nasopharynx to be able to protect you against infection. Now, we have a saying in the United States, I'm sure you have an Italian equivalent, of a game called whack-a-mole, where the whack comes up and you hit it and it goes down. We can't play whack-a-mole with variants. Otherwise, we would change our vaccine every 4 months, and we can't do that. And that's the reason why one of the main efforts that we're looking at is to try and develop a universal coronavirus vaccine that would be effective against any variant. However, even though we are at a very low level, and again, I had to answer that question a little bit ago to the press, we always must remember that it is possible How likely, I don't know, but it is possible that we will have a new variant that just when everybody thinks it's behind us, a new variant might come and essentially completely upend us. So again, I don't know the likelihood of that, but we need to keep an open mind that it could happen. In addition, probably one of the biggest surprises, and as a virologist and an infectious disease person, I was particularly impressed with this, is that a substantial proportion of the transmissions are from someone with no symptoms. That is completely against the paradigm of most respiratory diseases. Most respiratory diseases, you're near someone who's sneezing or coughing and you get transmitted. 59% of all of the transmissions from SARS-CoV-2 are from a person who has no symptoms, which makes contact tracing extremely, extremely difficult. Next, another thing we didn't fully appreciate, that unlike most respiratory infections, transmission occurs by aerosol, not a droplet that immediately falls to the ground, but a virus that can stay suspended in a population in a room, which is one of the reasons why there were these massive outbreaks that you saw at congregated meetings when it did not appear that anybody was sick in the audience. Lesson number 2, outbreaks are not consistently linear. In the first few weeks to a month of an outbreak, the increase looks like you're okay. And then what happens is that when you have a highly transmissible virus, you get an exponential increase. And that's exactly what happened in Italy, in the northern part of the country, and that's exactly what happened in the United States. When we had our first few cases, some in Washington State, some in Illinois, we were saying, be careful, even though there are only a few cases, it's going to be exponential. And we all know, to our great tragedy, that's exactly what happened. How do you counter that? The G7 and probably the G20 has set as an aspirational goal of the 100-day mission. What is the 100-day mission? It means to have a goal that the next time we get a pandemic threat, that we can be very quick within 100 days of having diagnostics, therapeutics, and vaccines. That's part of the pandemic preparedness plan, which is what I have been working with Rino Rapparoli with in what he and others are trying to do about getting enough knowledge about various families of pathogens to move very, very quickly. Lesson 3, again, another question that I was asked just a little while ago by the Italian press. It is essential that there's global information sharing and collaboration with everything from patient samples to surveillance data to research reagents to viral isolates. The definition of pandemic, pan, stands for all, which means it's throughout the world. So it doesn't make any sense, if you're trying to deal with a pandemic, that every country in the world is completely transparent in sharing all of the information that they have available to them. Lesson 4, leverage already existing infrastructure. Let me give you a good example. About 40 years ago, in association with HIV, I established the largest clinical trial network in existence, namely clinical trial sites in hospitals in the United States and throughout the world that could do studies on HIV vaccine, HIV prevention, and HIV treatment. They were already in existence. As soon as COVID came, we essentially transformed them into a COVID-19 prevention network, which allowed us to test tens of thousands of people in vaccine trials overnight. If we didn't have that, it would have taken years. And these are some of the sites throughout the United States here, but also throughout the world. And that allowed us to do something that was unprecedented. Lesson number 5. I'm going to spend a couple of more minutes on lesson number 5 than the other lessons, because as a scientist, I think this is one of the most important lessons to learn. That prior scientific advances and investment enabled us to do something that was entirely unprecedented. And I wrote about that in a commentary in Science magazine in April of 2021. And the title of my commentary was "The Story Behind COVID-19 Vaccines." And it's a very interesting and provocative story. Namely, the speed and efficiency with which these highly efficacious vaccines were developed and their potential for saving millions of lives was due to an extraordinary multidisciplinary effort involving basic, preclinical, and clinical science that was underway under the spotlight, under the radar screen, literally for decades before COVID came. So let me explain that story, because it's a very interesting story. There were two things that made the vaccine possible: a vaccine platform and a vaccine immunogen. I'm sure most of you are aware that a vaccine platform is, for example, is it a whole-killed? Is it an RNA vaccine? Is it a recombinant vaccine? Is it a viral-like particle? Any of a number of these. The vaccine immunogen is, what are you dealing with? Polio, measles, mumps, hepatitis. So how did this evolve? The COVID vaccine platform that was highly successful was mRNA. Most people thought, incorrectly, that as soon as COVID came, we decided to start developing the RNA platform. Not so. In fact, the classical study that allowed the mRNA vaccine was a study done by Drew Weissman and Katie Carrico. Look at the date of this paper, 2005. 18 years ago, they showed that if you modify the RNA molecule so that it won't induce an inflammatory response, you would have a very, very good vaccine. That's the first thing. What about the immunogen? This is work that was done on other diseases for decades that actually turned out to enable us to literally, in a few days, begin the development of a COVID vaccine, something never been done before. Let me explain. The Vaccine Research Center at the NIH, at my institute that I just left, was established more than 20 years ago. And there were two investigators, and this is the beauty of science. When you bring scientists together in one physical place where they can interact with each other, even though they have different skill sets. So more than 20 years ago, in trying to develop a vaccine for HIV, we established under President Clinton a vaccine research center. And I brought in people from all over the country with different skill sets. Two of these right here was Barney Graham, who was interested actually in respiratory syncytial virus. This investigator, Peter Kwong, was a world-class structural biologist doing cryo-electron microscopy to get the right configuration of a molecule. Peter, shown here, Peter Kwong, had worked for years trying to stabilize the HIV envelope protein in order to keep it in the right conformation for a vaccine. That's the good news. The sobering news is that we still don't have a vaccine for HIV. But his technology, working with Barney Graham, is that Barney Graham, who was interested in respiratory syncytial virus, used the technology that he learned from the structural virologist to stabilize a certain protein in respiratory syncytial virus called F protein, to stabilize it in its highly immunogenic form. So let me explain this for a moment. The prefusion protein is the very immunogenic. The post-fusion protein is not, and it's this one here is very unstable. So if you stabilize it by a few mutations, you get a perfect immunogen. So what has that got to do with COVID? Well, seemingly nothing, because what it did do, it allowed us to develop, in fact, Rino Rapparoli was involved with this, in a highly effective RSV vaccine. But the technology that was used was transferred when we were trying to make a vaccine against MERS. And I showed you a few slides ago, MERS is a coronavirus that also infects people from a bat to a camel to a human. And we were able to show that if you use those same mutations to stabilize the immunogen, you have a perfect vaccine. We never fully developed the MERS vaccine, but when COVID came along, all of the work that had been done for previous years was utilized to stabilize the now famous spike protein of SARS in its prefusion form, which was the perfect immunogen. So people ask you, how is it possible that you learn about the virus on January 10th, and 5 days later, you're starting to make a vaccine? And the reason is because you already knew what the important mutations were to stabilize the molecule. And as a matter of fact, these are the vaccines that have been developed by the United States government. Other countries have done that also. But notice one thing. The common denominator is this spike protein that was developed by Dr. Graham and Dr. Kwong very early on, associated with other diseases. That was an amazing success story. So what did that allow us to do? This is a very, very interesting and important slide because it really shows something that's completely unprecedented. As I mentioned, on January the 10th, we were able to identify what the sequence of the virus was. 5 days later, I called my team in my conference room at the NIH and said, let's start making the vaccine. And we partnered with Moderna, and 65 days later, we were in a phase 1 trial. 139 days later, we were in a phase 2 trial. 198 days later, a phase 3 trial. And 11 months later, we had shown that the vaccine, which we had tested in tens of thousands of people, was both safe and highly effective. 11 months. That is completely unprecedented in the history of vaccinology and biomedical research. Again, because of the investment that was made for decades. So let's compare that with some of the vaccine experiences that we've had in the past. So if you look from the time a pathogen is identified to the time you have a vaccine, it's ridiculous with typhoid. It was 105 years. Well, that's because we didn't have vaccine technologies, to be fair. But look how long it took to get a polio vaccine, 47 years. Pertussis, 42 years. Rotavirus, 33 years. Going down the list, look at COVID-19, 11 months from the time we had the sequence. The reason that's so important is that if it had taken us 5 years or 7 years to develop a COVID vaccine, just imagine how many more deaths that there would have been globally had not that been done. And I think this is the strongest argument you can give for a consistent investment in basic and clinical biomedical research. In fact, the Commonwealth Fund in the United States did an estimate that from December 2020 until November 2022, the vaccines have saved 3 million lives in the United States, 18 million hospitalizations, and more than $1 trillion in healthcare costs. So that is my response to the anti-vaccine movement. Okay. Now, Science Magazine has deemed that accomplishment the scientific breakthrough of the year for 2020, and Time Magazine, I think appropriately recognized the scientists, Drew Weissman and Katie Carrico in the top of the picture, who developed the mRNA vaccine, and Barney Graham and Kazmia Corbett, who developed the immunogen. Put those two things together, and you have the vaccine that each of us, I hope, in this room have actually been vaccinated with. Lesson 6, what we refer to as the priority pathogen and the prototype pathogen approach. What's the priority pathogen? That means a priori, you pick out a pathogen that you believe has a high degree of pandemic potential, and you already start making a vaccine for that. The WHO blueprint has picked out several priority pathogens like Crimean Congo hemorrhagic fever, Lassa, Nipah. That is predicting what will happen. But when you don't know what is going to happen, you do the prototype pathogen approach. What do you mean by the prototype pathogen approach? There are about 20 or 30 families of virus that have potential to be pandemics. It's going to be logistically difficult to study all 20. But if you narrow it down to about 7 or 8, you have a group that is workable. And what do you do with that group? You study individual pathogens within that, and you build on the prior experiences that you've developed in studying them. We put this forth as a concept several years ago. The first time we discussed it is a paper that we wrote back in 2017. But the brains behind it, the concept, belongs to Barney Graham in our institute, who very, very clearly delineated the conceptual reason why this is important. And what we did is we picked out 8 families. And what we're going to be doing is taking an individual representative pathogen from that, and already, before you have an outbreak, is to go ahead and study the basic virology, develop assays, develop animal models, develop antigenic targets, optimal platforms, immune correlates, so that if one of these here in this family becomes a pandemic pathogen, you already would have a head start. And as a matter of fact, if you think about it, that's exactly what happened with the coronaviruses, because we were working on SARS-CoV-1 ever since 2002 and 2003, and then with MERS in 2012. So that is the psychology and the strategy for pandemic preparedness. Lesson 5, another very important lesson. increase attention to the human-animal interface. 75% of all of the new pathogens that have afflicted mankind are zoonotic, which means they've jumped from an animal reservoir to a human. Human health is intimately connected to the health of animals. History is awash in those examples. HIV, chimp to human. Influenza, bird or pig to human. Ebola, bat, non-human primate to human, and on and on. So what we need to do, as I've written about in Cell about 3 years ago, is we've got to take a very close look at how the human species negatively impacts on the animal-human interface by encroaching on rainforest, by having the intermingling of wild animals that you don't know what the viral capability within that or the reservoir. And that's the reason why right now we don't know what the origin of COVID is. We have to keep a completely open mind. Was it a natural occurrence? Some people talk about a lab leak, but if you look at the data that has recently come out from an international group of evolutionary virologists, the data strongly suggests, but does not prove, that it was a jump and a natural jump from an animal to a human. But given the fact that we don't know definitively, even though data such as these data that have just come out from these evolutionary virologists, we have to keep a completely open mind so that we can prevent it, hopefully, from happening again. But given the assumption that it might be a jump from an animal to a human, how do we mitigate the risk? One, you increase surveillance of the interface between animal humans. In the United States, it's referred to as One Health. The health of animals is important, related to the health of humans. Number two, pay attention to the clearing and degradation of tropical and subtropical forests, because that's when you encroach upon the animal-human interface. Improve the health and economic security of communities whose living depends on an interface between animals and humans. Enhance biosecurity in animal husbandry, and please, and we've essentially pleaded with certain countries, including in Asia and China, to shut down or strictly regulate the wildlife markets. Lesson 8. This is probably true throughout the world, but in the United States, the long-standing systemic health and social inequities drive pandemic disparities. In the United States, African American, Hispanic, Native Americans have a much higher rate of severe disease due to what we call the social determinants of health. In other words, they have a higher incidence of the diseases that lead to a poor outcome. How do we overcome that? Address discrimination, address the limited health care access. I got asked questions by the Italian press. Why did America do so poorly if you're such a developed country and you have 1.13 million deaths? These are some of the reasons. The occupation of minority populations put them in close proximity to a virus. The educational income and wealth disparities, and things like housing with multi-generational families are not able to separate when one person in the family has an infection. Lesson 9. Misinformation and disinformation is unequivocally the enemy of public health. And I think we're starting to see that essentially all over the world. The conspiracy theories, the misinformation that spreads like wildfire. One misinformation that has spread throughout the social media is that the vaccine has caused more deaths than COVID, which is completely ridiculous, as we all know. but there are many, many instances now of the social media spreading false information. Okay, lesson 10. Some of you may have heard of Yogi Berra. Yogi Berra is an Italian-American baseball player, and he was noted for some very interesting sayings that he would say. One of the things he would say, seemingly obvious, when someone says, "Is it over?" in a baseball game. It's the last inning, you're winning by a lot. And he would always say, "It ain't over till it's over." And that's really what we're going to be saying about COVID. What do we mean? What's the end game for COVID in 2023 and beyond? I tend to look at it by asking, what are the possibilities? Are we going to eradicate COVID? Are we going to eliminate COVID? Or are we going to just control COVID? So let's take a look at eradication. Eradication means you eliminate it from the face of the earth. So in my opinion, and those of most infectious disease people, the chances of eradicating COVID is zero. And the reason I say that is that we have only eradicated one viral pathogen in the history of the earth, and that is smallpox. Now, why were we able to eradicate smallpox? Smallpox has two characteristics that make it amenable to eradication. One, it is not changes. It's phenotypically a stable virus. The smallpox that killed some of the Roman emperors that we were looking at in the archives outside centuries ago is the same smallpox that we eliminated in 1980. So it doesn't change. Number two, if you are either infected with smallpox or vaccinated with smallpox, the duration of your immunity is measured in decades and likely for a lifetime. So hold on to that for a moment. The next question is, are we going to eliminate it? Elimination means it's no longer in Italy, it's no longer in the United States, it's no longer in the European Union, but it may be in some lower and middle income countries. Are we going to eliminate it? Highly unlikely. Why? Take as an example measles and polio, two infections that have been eliminated in the United States. So even though there's polio in some developed countries, and even though there's no measles and no polio in the United States. How did we do that? Number one, measles and polio are stable viruses. You don't have multiple variants like I showed you on a prior slide. Number two, similar to smallpox, when you get infected with measles or vaccinated with measles, the duration of your protection is measured minimally in decades and maximally for a lifetime. So now let's look at SARS-CoV-2. How different is it? Number one, it's a phenotypically and genotypically unstable virus. I just showed you multiple slides of multiple variants. So one of the prerequisites for eradication and elimination is not there. Number two, the durability of protection. We all know that of SARS-CoV-2 infection or vaccination. Instead of being measured in decades, it's measured in several months to a year. So what can we hope for? We can hope for control. And what do we mean by control? And that relates to a question that one of the members of the Italian press asked me. Is COVID over? And that's when I said, it depends on what you mean by over. Namely, that we still have it in our society, but it is at such a low level that we call it endemicity, we call it return to normalcy. We know we're practically normal. I was out with my wife walking through the streets of Rome, and there are tens of thousands of people in restaurants, having coffee or a beer or something, no mask, which is good because the level of infection is very, very low. Namely, if it remains similar to certain viruses that we accept in a way that does not disrupt the social order, then that's what we mean by acceptable control. So going beyond COVID, forgetting COVID for a moment, the question again that I get asked, what about other potentially pandemic pathogens? What can we say about that? Getting back to my old friend Yogi Berra, I was very much of a fan of Yogi Berra. I wrote a paper in the New England Journal of Medicine just a few months ago, and I entitled it, "It Ain't Over Till It's Over," because it's never really over. And what I mean by that we don't want to be going around worrying all the time about what's going to happen. But the one thing that is clear is that the threat of a pandemic has been with civilization from the beginning of civilization. It's been with us through recorded history, and we've just spent the last 3 years experiencing one of the worst pandemics in the history of the world. And so, if you look at how this evolves, 38 years ago, when I first testified before the Congress of the United States, I showed the map of the world and I said, HIV is a brand new infection that's emerged. And every year, over 38 years that I testified before our Congress, there was always 1 or 2 or 3 new infections that were either brand new or reemerging. The last time I testified before the Congress, which was just a couple of months before I stepped down from the directorship, this is what the map looked like. Some of these are trivial and inconsequential, but some of them, like Ebola or Zika, of course, COVID, have transforming effects on society. So on the last slide, I refer you back to a paper that I wrote a couple of decades ago, and that was entitled Emerging Infectious Diseases, a Perpetual Challenge. And the only way you address a perpetual challenge is by perpetual preparedness. And that, to me, is the major lesson of COVID-19. Thank you.